Hello guys, welcome back to my channel. My name is Joseph. So today what we are going to do is that we are going to take a deeper look at a simple one-dimensional population balance. By one-dimensional, we mean that we are going to take a look at a population balance equation that is one-dimensional in terms of the internal coordinate. Or for example, if you say that you are modeling a crystallization system, then it could be the size of your crystal, right? So we are going to look at a population balance equation that is one-dimensional, not in the physical space, but in the internal coordinate space. So let's jump straight into it. So let's just first do a quick recap on the general population balance equation for a continuous and deterministic system. So what we meant by continuous and deterministic system is that if you are dealing with a particular process, for example, then the number of particles in your system throughout time and throughout the internal and external coordinate space, or the physical space and the internal coordinate space, such as your particle size, the space that represents your particle size, for example, must be abundant enough so that the entire behavior of the system can be assumed to behave as a continuum. So that is first and foremost the population balance equation that we are talking about. There are many other versions of the population balance equation, but you can refer to some other excellent review papers that specifically discuss on the different types of population balance equation. But here, what we are looking at are the continuous and deterministic type of population balance equation. So the general population balance equation that we have here is shown here, right? This is what we have looked at the past video. So there are a few terms, a few primary terms in the population balance equation. So the first term here tells us how the number density evolves with time. So you have the partial derivative of the number density with respect to time. The second term here tells us how the number density evolves with the internal coordinate space. So as we mentioned in the previous video, let's say if you have a system, again we use a particulate system where your particle is capable of growing or shrinking with time, then you would have this so-called velocity through the internal coordinate space, and then you would involve this term in order to model that growth or shrinkage of your particle through the internal coordinate space. So this is represented by the second term in the general population balance equation, and this x dot here is the velocity of your particle, or in other words, the growth rate or the shrinkage rate of your particle with respect to the internal coordinate space. So the third term here is the term that tells us how the number density evolves with the physical space. So here you expect that if you have a fluid that is moving, then your particle will be moving with the velocity of the fluid. Then you'd have, this is the velocity of the fluid, and then you'd have the particle moving throughout the physical space. So this term actually accounts for that. So if you wanted to model your system, and it is important enough for you to track the movement of the particle throughout the physical space, then this is a term that you would deal with in the population balance formulation. Alright, but if your number density of your particle, you consider them to not be dependent on the spatial coordinate, then you can drop this term and just model the entire system as a system that is purely dependent on the internal coordinate space. Okay, so it's essentially it's just a well-mixed system that you're trying to model. And the first term on the right hand side here is the birth or the depth term, or usually we say that this might be the sink or the source term, where you actually account for additional physics like the aggregation of the particles. So two particles joining together to form one larger particle, or you can have one parent particle breaking into smaller particles. So the aggregation and the breakage term is being accounted for in this term, the first term on the right hand side here, which is your sink and the source term. So this is the general population balance equation that we spoke about in our previous video. But in our video series here, we are more interested, or rather I'm more interested in actually going into each term and let's study them in detail to understand the population balance equation better, so that we can apply them more appropriately, right? Instead of treating them just as an equation, we want to learn everything that we need to about the population balance equation so that we can actually use them more efficiently and use them, more importantly, to use them correctly to model our process of interest. So in this video, we are going to look at how a 1D population balance equation can emerge just by considering the concept of a number balance. So remember that in our previous video, we spoke about that the number density is the thing that we wanted to model by using the population balance modeling approach. So here we have the
I want to say something because I feel it may be very difficult for you to catch the idea, but if you think in the other way, you will find it's much easier. In the population balance model, you realize that the x is the internal coordinate and r is the external coordinate. In other words, this two is actually, I shouldn't say actually, I should say these two is similar to each other. It's one describe the external coordinate and the other describe the internal coordinate. Nevertheless, it's probably very difficult for you to understand what's internal coordinate. But on the other hand, it's easy to understand the external coordinate is the position, right? So if you first try to understand the population balance model by understand the external coordinate, the position, and then you use your imagination, you may think treat or you can count this internal coordinate, something like the external coordinate, then you will be easy to understand this model. Okay, so first thing, you can neglect the internal coordinate, but focus on the external coordinate. So you think about the equation is some particles move around in the space. And then after that, you get this idea, and then you apply the idea to the abstract internal coordinate.
Number density function, right? This is the thing that we are actually after. And the number density function, we have also introduced the fact that it is in general, if we actually write them in general, it is a function of the internal coordinate, which can be your crystal size, the age of a cell, or the degree of polymerization of your polymeric system. Right? So it's a general function of the internal coordinate as well as the external coordinate, which is your physical space. Okay, and it can also be a function. I mean, very obvious. We wanted to model it. We wanted to model how the number density actually change with time. So it has to be a function of time. Okay, so this is the number density function that we are after for our process. Whatever process that you are dealing with, this is the term that you are going to want to be focusing, right? You wanted to model the evolution of the number density throughout the internal and external coordinate space and with time. So the number density function here, it tells us the number of particles per unit volume of the physical space. Okay, and per unit volume of the internal coordinate space. So we say per unit volume of the internal coordinate space here, but in general, the internal coordinate space can be multiple dimensions. It can be more than 3 dimension, 4 dimension, 5 dimension. But in general, if we consider this as a volume, the entire domain throughout all the internal coordinate space, we consider this as the volume. In the physical domain, it's easy for us to imagine because we always have the 3 dimension in our physical space, and we straight away we know that by our physical intuition that the volume of the physical space is a 3-dimensional volume. Right? But in the internal coordinate space, you can have more than 3 dimensions. So whatever it is, the entire space is what we call the volume. Okay, so in trying to understand how to construct a population balance equation by considering the balance of the number of particles, we need to be able to speak of the concept of particle fluxes, right? It's just like what we have done for transport phenomena. When we build the continuity equation, we actually talk about the mass flux, right? We say that the mass density, the rho mass density multiplied by the velocity of a fluid, for example, the mass density multiplied by the fluid velocity will give us the mass flux, right? And then in the Navier-Stokes equation, we talk about the momentum flux. And in the energy equation, we talk about heat flux and so on. So in order to construct a population balance equation, which we say is based on the idea of the balances in the number of particles, right? We need to be able to consider the idea of particle fluxes. So in this case, because our number density is a function of the internal coordinate as well as the external coordinate, we need to be able to consider that the number of particles, the fluxes of the particle, can be through the internal coordinate space, which means that your particles can be growing or shrinking, right? It changes in size for that same particle, right? That specific particle, over time, it can grow or it can shrink. So we need to consider the particle fluxes over the internal coordinate space. And at the same time, if we are considering that the particle can move with time through the physical space, then we need to also consider the particle fluxes through the external coordinate space or our physical space. So these are the two fluxes that we need to consider. So analogous to the concept that mass flux is just the mass density multiplied by the velocity of the fluid, here the particle flux is just the velocity through that particle space that we are talking about. For example, if you are talking about the flux of the particle through the internal coordinate space, the flux will be just the particle velocity through the internal coordinate space multiplied by the number density function. So x dot multiplied by n will give us the particle flux through the internal coordinate space, and then the
I get some ideas. I always try to think in your position, okay? So I kind of believe you guys may have a difficulty to understand why it's in this way. So let me do a survey, okay? How many of you know why it's x dot and then multiplied by this one? If you can understand, raise your hand. No. Okay. So why would be in this way? Let me introduce something to you. Okay? That will be much easier than direct digest this. This one. I can't forget about it. How many of you know the chemical master equation? Chemical master equation? No? Okay. Let me show you this. So it's called a master equation or called a chemical master equation. We call it a chemical master equation, okay, because we are chemical engineering. That's to let me find a easy version for you guys, okay. Probably this one. I use something still look difficult for you to explain this. Probably I should write it myself. Okay, let me write it myself, okay? But if you want to understand the chemical master equation much more, you can go to Wikipedia. The usual Wikipedia will write down the canonical form, or probably I should say the journal form. But this equation is kind of easier. Let's first write down a one-dimensional chemical master equation. So you try to get this thing. That's too funny actually. No. Let me don't do it like in that way. Let me do it in the easy way. Okay, so let me. So before we try to understand the population balance model, I want you to understand the chemical master equation first. And this is a chemical master equation, and you can go to Wikipedia and type in chemical master equation or master equation, and they will give you some equation that does not look very friendly. But nevertheless, I give you a friendly chemical master equation. It describes only one-dimensional. And so in the chemical master equation, you have many reactions, just as we did in reaction engineering. But in reaction engineering, we describe the concentration, not the probability. So it's different ideas, okay? Different concepts. If you describe the probability, if your reaction is if this reaction will cause the particle X particle to decrease. -1, so it's decrease 1 particles. If the reaction decreasing 1 particles, then you need to multiply by the probability with S plus 1, right? Because Oh, probably 3 weeks ago, we have this one, right? Another time we deal with I don't remember what exactly we deal with, but in my memory we get a velocity profile, right? And also we get the shear stress. Do we calculate the average velocity? Hello? Anyone there? Do we calculate the average velocity? Yes. So we also in talking about the force, right? Okay. So we finish this example. Okay, good. Yes. Please forgive me about this because I have the other advanced full mechanics, so it's very difficult to. Okay, no, the other one does not have battery. So probably I put here. Hopefully, they will change your battery. to the previous example, but I prefer to write down. Okay. In textbook it does not write down. Okay, so yeah, sure. And as usual, I will give you some time to write down the notes. So, yeah. So if you don't want to write notes, you can compare this one with the previous example, okay? With the previous example, and see if you get something interesting out of this. And for the one who even don't want to compare to the previous example, probably you don't even want to compare to the previous example. Let me say some joke or something to you. So as you know that I went to participate the YAPEC conference in Busan, Korea, and then I kind of believe many of you know what's the most famous food in Busan. That should be the pork soup. Okay, so everyone go to Busan will definitely go to eat the pork soup. Okay. The funny part is this part. Okay. I saw the Google review. So in the Google review, the people say that the pork soup is without flavor, or it's not salted. Okay, it's not salted, but the sauce is very salty. Let me say this again. So some review, especially from a background similar to us, they say that the soup is not salted, but the sauce is very salty. And if you know this soup, the pork soup, then you know this is kind of funny. That's not sauce. That's sauce. Okay, it's not the common sauce we think about. It's actually more like an ingredient, and that thing is used to add into the soup. It's not used like a sauce. We don't use that sauce to eat the pork. That sauce to eat the pork, but we use that thing as an ingredient to adjust the salty of the soup. So those people who didn't know that, and then they just say some malicious words against the store, the restaurant, about why the soup is not salted, but the sauce is salty. kind of stupid. Okay. Still have some people writing. Probably I can explain that in Chinese, so you guys will not make this kind of mistake. 所以我不知道你们有没有去过釜山啊？如果你们去过釜山，应该吃过。如果去的人，大家都会去吃猪肉汤啊，非常有名。但是网络上有一大堆来自我们的同胞们写的评语哦，看得非常莫名哦。他就会写说猪肉汤是没有味道的，那可是它有一个酱非常的咸。但是如果你吃过猪肉汤，你问过韩国人就知道那不是酱哦，那东西是用来调汤的咸度的。 可他们把它当做酱，所以非常的非常的搞笑。所以跟大家讲一下，如果大家有去韩国吃猪肉汤，看到一个长得都是虾子的那个是用来调汤的咸度，那个如果不加进去，汤是不会咸的。然后不要留这样的评语哦，真的非常非常的伤害那些餐厅哦。其实人家做的很用心这样。OK，let me come back to here. Nearly everyone finished. So this example, it actually take the shell, but the shell is very similar to the previous example. The only difference is for this control volume, your R can only be between the kappa R and the capital R, okay? So the kappa R and the capital R. All right. And then we can easily write down the force balance. So the force balance is kind of easy. If you try to describe the phi RZ, then you need to multiply by the area, right? So the area normal to R. So that should be 2 pi R L. If you have difficulty, let's take a look at this. You have phi RZ. Phi RZ is in this way, right? And the face normal to that should be the white here. Of course, it is half of that. And you don't need to worry about the inner tube, okay? Because it's not in the domain. So you still have this kind of control value. And then you try to multiply by the inner area, this white area. And this should be 2 pi R. 2 pi R will give you this one, right? And then multiply by L. So it's 2 pi R L. So it's 2 pi R L. Alright? Kind of easy to understand, right? And for the other force, it should be the phi ZZ, right? Phi ZZ is supposed to act at the area normal to Z. So that should be this smaller white. Of course, it is half of that. But we know that this one should be 2 pi R delta R, right? We explain that this 2 pi R delta R, if you do the integration, you get a pi R square. So that perfectly describes the area here. Okay. And so we have two force. Two force comes from the combined momentum flux, and one from the gravity. And I put a GZ here because in this example, where flow is from the top, from the bottom to the top. And the gravity is supposed to in the opposite direction, right? In the opposite direction. But when we first write down the equation, usually we just write down GZ to describe the gravity in Z direction, okay? And then next one, we analyze the GZ, we know it should be a negative G because it's in the other direction. And then we also do the same thing with all the examples. We divide by the control volume, and then also we let delta R approach 0. And in previous example, we explained that we cannot divide by R, delta R, right? Because that R is different for this one and this one. So we cannot divide the R. Okay. And then we divide that, and that delta R approach 0. And once the delta R approach 0, this thing will become the partial derivative of R phi RZ, right? R phi RZ. And for the right hand side, we have these two terms. And we have a negative term here, right? Negative term here. Because, not negative term there. Because GZ is minus G. So we put GZ is minus G here. Huh? Let me make sure I didn't make a mistake. No, I didn't make a mistake here. Okay. So we have a minus 10 here. Okay, so here is, we put this on the other side. So that's why we have R delta R at the first and then R at the second, different from this one, right? But for the rest, it should be the same, Z, zero, and then minus rho G. Okay. So we have this one. All right. And after that, we try to analyze the system. And of course, we cannot directly deal with the phi, so we try to separate the phi into P, tau, and velocity. And also, we can rewrite the tau into velocity. So we do it this way. First, for the phi ZZ. And similarly to the previous example, we know that for the velocity in z direction, because it's incompressible flow, and also it's the cross section area does not change there. So the velocity at the z direction, velocity along with z direction does not change there. Okay. It means that the phi z does not change there as long as the r direction is given. Okay. And for that case, if you put this thing into here, and since the only difference between these two is the z direction, right? Is the z direction. One is at the z equal to 0, the other is at the z equal to L. So if you put this into here, this minus this will be 0 for this term, right? Because the Vz does not change along with the z direction. It's clear, of course. If not, let me know, okay? And since we know that the Vz is not changing with z direction, this term should go to 0, right? Because it describes how Vz changes with z direction, right? But Vz does not change with z direction, so it should go to 0. So finally, we only have one term left, this P. Okay, for this phi ZZ. Okay, so we know that. We will put that here somewhere. I will write that down, okay? Next is the left-hand side. The left-hand side, phi RZ should equal to tau RZ plus rho VR VZ. We know there is no VR. Because VR is flow in this direction. It will directly penetrate the well, the tube well. If we don't have this kind of flow, we don't have the VR. So we don't have VR. And since we don't have VR, this term will go to 0. So we only have this term. That will be put here. All right? So let's continue the example. Any question about this? No? Okay. Because many times people will ask about this VZ， so let me explain in Chinese, okay? 就是这个 VZ 不是零啊，不是零，但是因为它不随着 z 方向增加或减少，因为我们假设它是一个不可压缩的流体啊。那因为这个原因的时候，你放进来这边，因为它只有 z 方向上的改变哦，那所以你这个放进来跟这个放进来这里，它们两个相减以后就会是零，所以 VG 自己不是零，但是两个相减以后是零，好不好？这样应该 OK 了哈。OK, all right. Now let's continue this example. this microphone, probably the school will complain about this. So it's, the microphone like to, I shouldn't say like to, the microphone sometimes will automatically shut down by itself because of the low battery. So hopefully that people who watch the video will not complain about this. It's something I cannot control though, okay? This is belong to the department office, and they are in charge of it. The only thing I can do is complain to them. So anyway, and I think I believe they did a good job. So they tried to give us the new microphone at the beginning of this semester, but those new microphone does not work well, so they have no choice but give us those old microphone. Okay. Yeah. Yeah. So that's why I say about the other, the bird. So this is not real boundary condition. It is, but it does not stop the question. Okay, it just postpones the question and then wait until get the real boundary condition. Yeah, and why the author of this book do that? Because they try to get some physical meaningful parameters. So think about it. If you use C1 and you calculate that with C1, it's correct. And then after that, you get a velocity profile. You try to solve the C1 and also the other integration part, constant C2. Nevertheless, if you do it that way, the C1 is some number that's without any meaning, right? So the author try to postpone that boundary condition, but give the meaning to this lambda. That's the whole idea. Yeah. Okay, I cannot believe all of you finished that. So here is, as I explained before, the author don't want to use a C1. So he actually assigned some physical meaning for parameters, which call lambda. And then he used his idea to say that if r equal to lambda r, the tau r0 equal to 0. And it is, of course, right. And he tried to replace this R with replace this C1 with R, sorry, by R. Replace this C1 by R. And then get some physical meaning for parameters. Okay. But this R is unknown right now. It's unknown right now. It can only be determined after he put a real boundary condition here. Okay. So he put it here. And then he tried to solve this R, and then he get R, and then substitute it into here. Sorry, try to get a C1, and then substitute it into here. So he get this thing with the lambda there. As we know that this lambda can only be determined later. Okay, let's have a break, okay? So in previous class, we said that after he replaced the C1 by lambda, the author get these equations, okay? If there's no other question, erase this and continue try to solve the velocity profile. And for this tau RZ, we should be use this one. So we get a tau RZ here, right? Tau RZ here. So we know tau RZ should equal to minus mu, rho VR, rho Z, and rho VZ, rho R. Nevertheless, we know the VR is 0. So rho VR, VZ should be 0, right? So we only have minus mu, rho VZ, rho R, okay? Right. Now, let me take a look at syllabus. Where's my syllabus? It's a wrong one. So bad. But I just want to see so we still have 1 week, one makeup class on November 1st, which is next week. And the video has roughly video about the population bands has roughly 30 minutes left, so there should be enough. If I don't say too much, we should be able to finish all the videos. Okay, so next week will be our last makeup class. And then we don't have class at midterm exam week. So next week we'll have makeup class. But November 8th is midterm exam week. We don't have class, okay? All right. And if you don't attend a makeup class, but you still want to learn something about population base model, you can go to the Taipei Tech High School and check the link. Did I upload the link? Probably I didn't. Yeah, I have memory to upload link in the other course, the other full mechanics, advanced full mechanics course, but I don't remember if I upload here. Anyway, I will share that. Okay. So if you want, I'll probably just show you here. So if you want a population-based model, you can take a look at this. That has a lot. Okay, I upload in the link. Okay. Okay. If you finish your notes, you can probably try to solve this by yourself. I didn't try that, so it looks not that friendly, so I didn't try it. But you guys can try it by yourself, okay? As usual, I wait for all the people to finish it. Then I probably say one story. If you guys go to Korean, you will not lose your life. I don't know how many of you know that Korean people, they like to eat the spicy octopus, the living octopus. How many of you know that? No? No? There's a famous dish, the living octopus. So the Korean people will pick up one living octopus, and then they will dip it in some sauce, and then eat it. So at the very beginning, I saw this is a very special food, and I want to eat that. And then I go to Korean, and then I ask some of my Korean friends, and they told me don't do that. So many people died of this dish. So the octopus, after you eat this, you will stuck your throat, and you are probably shocked to die because lack of oxygen. Kind of interesting, right? Okay, so if you go in Korea, don't eat that. And then the Korean people told you that, not Korean people is nice, but restaurants sometimes they told you that they use the part of octopus. And then you may think this is safe if you don't eat the whole octopus, but you just eat part of it. Nevertheless, it still kills people. Kind of interesting. The reason is octopus is not like us. They have so many brains. It's not only on or probably I shouldn't say so many brains. They have so many neural cluster. So it has the cluster everywhere. It's not only in the brain. So those cluster can do many things. And one of that is kill the people, eat them. So kind of interesting. Okay. Hopefully you guys finish your notes. Probably I can say one thing interesting. So if you go to Korea, especially Busan, you will see so many beautiful seafood, and one of that is the sea pineapple. It's kind of beautiful. It looks like a pineapple. It's very beautiful. And after the first glance, I was attracted so much by this food, and I desperately want to eat it. And then finally, I have chance, and then I ordered sea pineapple. I'm so happy that those food, I can eat this kind of food. But after I taste just one bite, it's so disgusting. It tastes like you eat some sea trash, and then you concentrate that flavor at least 10-fold or even 100-fold. It's so terrible, so terrible. And then I complained to the tour, the guide. I said, "Oh God, this is so bad." And he said, No, this is not so bad. You should try the stingy ray in Korea. Probably you guys didn't know that, the Hongyu in Korean. That's the world's second famous food. The most stingy food is in Norway, and the second one is in Korea. People say that food tastes like the flavor in the restroom, but concentrated tenfold. It's a special fish. Probably I should say fish. The stingray, the Hongyu. This creature, it has very interesting things. So after it dies, it will excrete the ammonia by its skin. So everywhere is ammonia. And as a result, this creature, you can store that even in a room temperature for half or for 1 year. And then the Korean people will do that. After 1 year, they will take this and then told you that this is a famous and delicious dish. Kind of interesting, okay. All right. Let's come back here. And after that, I feel the central egg is nothing comparing to them. Kind of interesting. Central egg is pidan. Okay, let's come back to here. So we put this dvz minus mu dvz dr in the position of the tau RZ, okay? So we have mu here and minus here. And then we try to solve the VZ. And except for this minus mu, the rest is tau RZ, right? Tau RZ. And then we solve the VZ, okay? We solve VZ and get the other integration constant. And then we apply these two boundary conditions. Try to solve the C2 and also lambda. And then those quickly solve that and get C2 is -1. And lambda is in this explicit form. No, so implicit form. So you don't get a lambda, but you get lambda with something, okay? And then the author just put this lambda into the equations because it's lambda squared, so we put lambda squared there. So easily, the author get this tau RZ. And similarly, they easily get this VZ. Hopefully it's clear to you guys. So any question about this? And after this, we will solve the, we will try to get, not solve, we'll try to get the maximum velocity, the average velocity, the mass flow rate, and the shear stress. Okay. It's all right, right? Okay, let's do it. for those part, it's okay. So if you finish your notes or you don't want to take notes, think about the shear stress, okay? Shear stress already show here. And see if you find something interesting. Think about the shear stress. Okay. Confused me for a little while. And then the funny thing is the bird, he don't want to explain it. He just said, oh, the reader should know that by himself. It's kind of funny. Let me quote his original word, kind of funny. The reader should explain the choice of sign in front of the shear stress above, and also give an interpretation of the final results. It's just that. That's the only explanation in the textbook. Say the reader should explain and also give the interpretation. So take a look at this shear stress and thinking about that. Okay, sometimes you may have a difficulty to understand what happened, but sometimes. But what I feel is all the question in fluid mechanics, if you think that as simple as possible, usually you get results, you get an answer. And if you complicated the question, then you don't get the answer. Okay, so try to think about shear stress as simple as possible. You may get the answer. I don't know how many of you know the bufferfish. Bufferfish? It's a very famous dish, the 河豚. It's because I think it's ancient people, Su Dongpo, say the bufferfish is one of the most delicious food in the world. And also, why I mentioned this, kind of funny. So this time in the conference, a scholar in Kaohsiung University of Technology, and he told me that he want to eat a bufferfish in Busan, and I was shocked about that. Because I know that we can eat the bufferfish in Keelung, just 20 kilometers away from here. So if you want to eat a bufferfish, don't go to Korea. You can eat that in Keelung. It will only take you less than an hour, and then you can eat a bufferfish. And to be honest, it tastes okay, but not delicious. I shouldn't say that way. It tastes delicious, but it's not the best food in the world. Okay, it just tastes delicious. All right. come back here. All people finished? Yeah. All right. So the maximum velocity should happen when when Vz at r equal to lambda r, right? Just as our I should say the first boundary condition. We just try to use this to replace C1, right? So we know the lambda r at this position. We should have the maximum velocity as shown here, right? So just put that there. No problem at all. The average velocity, we just do the integration, and we should be able to get average velocity. Hopefully that now you feel good about this. Of course, you can put the 2 pi r dr here. So some people they to do that. They put pi r dr there. That's a better form. Why? Because 2 pi r dr you get the area, and your average velocity should base on the area. So the 2 pi r dr is better than this one. You just write the r dr, okay? Because you want to integrate over the whole area. So usually we write 2 pi r dr. However, 2 pi can be cancelled out, so I didn't write that. And then you will get this one. My bad. And mass flow rate, it should be the area here, okay? Area here. So this 2 pi r dr also is integrated from kappa r to r. You don't integrate from 0 to r, okay? It's from kappa r to r. Because your domain is kappa r to r. Okay? So here also, you get an area, cross-sectional area, in between kappa r and r. Right? So kappa r and r, so you get a pi r squared, that's r. And the other is pi kappa r square. So you get a pi kappa square r square. Alright? So you use the whole cross-sectional area, the bigger one, minus the one inside here. So you get a cross-sectional area of this region. Alright. And then you multiply that by average velocity and multiply by the density, and then get a mass flow rate. All right. Any question about this part? Should be fine, right? It just looks ugly, but the concept is clear. Nevertheless, let's deal with this real question. So you take a look at this shear stress. Does anyone feel strange about this shear stress? Thinking about that, your shear stress, the shear stress of the wall to the liquid are supposed to pull the liquid from moving forward, right? So you know the velocity here is 0, velocity here is 0. So the wall definitely give the fluid some force. And this force prevents the fluid to flow, right? That's correct, right? Nevertheless, if you take a look at the shear stress of the fluid on the wall, you'll find these interesting things. You catch the idea, right? We know the force is in one direction. It should be these two. I mean, at this position or at this position, the force should all in the same direction. But your shear stress is in different direction. What happened? Let me say again, okay? we all know that this tube wall, it will prevent the fluid to flow, right? Because the velocity here is 0. So we know the force for the wall to the fluid should be pulled down. Okay? And force of fluid to the wall should be lift up for both walls. Nevertheless, you take a look at this shear stress, you find something different. This two is in a different side, in the opposite side. So how can it happen? Is that implied the fluid here, for example, the fluid here is trying to lift the wall, but this one is trying to push down the wall. Is that the real case? And then also only give us one sentence. I read that again. The reader shall explain the choice of the side in front of the shear stress, and also give the interpretation of the final result. So, anyone? Just try. Yeah. Really? But if you take a look at here, your shear stress are all at one side, right? Even, but here shear stress is in different side. How can it be? If it's in different side, is the fluid give the so probably you can think about that. It's the force of the fluid on the wall here, and the force of the fluid on the wall here in the opposite direction. But if it is in that way, how can it be? Yeah. Yeah, both of you interpreted the maximum velocity, but now the question is why is in the opposite side? You mean this one? Oh, you get this one. But think about it. Even is in this way, right? Can be all positive, right? Why is one positive and one negative? Huh. Oh. Okay. And okay. Okay, anyway. Yeah.
内地到大速度的时候，它速度是怎么增加，所以它的缺水是，然后最大速度到外地的时候，速度会减少，所以它的缺水是。
Yeah, mathematically is correct. So how about you two get a point? Yeah, so what I say is I kind of believe more close to what the author want. And you also point out a very important point. So what I say is you find the velocity gradient here is different from the velocity of gradient here, because this is increase, this is decrease, and your shear stress, as you know, is minus. Your shear stress Vz is minus u dVz dr. And since you have the different velocity gradient, you definitely have different side of shear stress. Your velocity gradient is in different side, right? So your shear stress should be in different side. Okay, great. All right, thank you. Okay, now we have 10 minutes. Let's go to the next example. So next one is try to deal with the problem in an interesting way. He said that you have two plate. It's not tube, okay, it's plate. You have two plate and you have 2 layers of flow. So one layer is on the top and one is at the bottom. You have 2 layers of the plate, the flow. And then we try to solve the shear stress and velocity gradient of this one. Okay. Okay, so let's try to do it. Before we did, we should realize that for this example, we can take the control volume, but the one above here and the one below here is a different fluid. Okay, so for the different fluid, we should have different viscosity. And then so we need to formulate the 2 equations. One is for the above, the other is for the bottom layer. So we have the top layer and the bottom layer. So we need to formulate the 2 equations. And then if we need to formulate 2 equations, we actually need 4 boundary conditions, right? 4 boundary conditions. And as we explained in the previous example, this, if we use this as a boundary condition, we finally need to replace. We need to replace this boundary condition because this is not given the information. So we need a 4 boundary condition. And we can quickly note 2. One is at this, the interface between the bottom flow and the plate, the velocity of fluid should be 0. And the other is this, the velocity here should be 0 also. Okay? But still we need 2 other boundary conditions. And also use a very beautiful boundary condition, I would say. So what he says is, think about that. Even you have two fluid, at the interface of these two fluid here, okay. If you apply the same idea of this one, if you apply the same idea of this one or this one, you realize that for the fluid A, fluid 1 and fluid 2, they should have the same velocity, right? At this point. That's the same boundary condition we apply here. Why we say the velocity is 0? Because the plate does not move, right? So it has the same velocity as plate. But here, although both fluid flowed, but at this point, they should have the same velocity. It's just like it has the velocity here and here. Otherwise, you will have the discontinued points here. But anyway, they say you will have the same velocity. And also, you should have the same shear stress. Okay? Because if you have the same velocity, and the shear stress here, the fluid, because of the Newton's third law, so you actually have the same shear stress. Okay. So with these two boundary conditions, we totally have 4 boundary conditions, and we have 2 equations. So we should be able to solve these equations with 4 boundary conditions. So let's do it after a break. Okay, we should have a break. Yeah. See you after a break. Okay, let's compare two cars. Oh yeah, and I seem to forget to write down the force. So although he perfectly explained the side of the shear stress, but what will happen to the force? Similar question, why there's a negative side? But it's actually, let me wait for all the people to finish it, okay? And probably I also give one story since I just come back from Busan. So I kind of want to share many information with you guys. So if you go to Seoul, the capital of the Korean, you know there's the City Wall. If you go there, the City Wall is very beautiful. It's near the eastern gate. It's very beautiful. But even the Korean, not much of them know that Busan has a city wall. And that city wall is even better than the view is even better than the one at Seoul. So if you go to Busan, probably you will not see this information on website, but please to go to a city wall. That's one of the best view in Busan. Okay. All right. Let's come back to here. So we actually have a negative side here. And this is what I want to ask when I ask this thing. But both of your classmates give a very good answer. One is from mathematics, and the other also from mathematics, but it has some insight of the velocity and the shear stress. But this one, but both of them, actually, cannot explain this negative side, right? It explain the negative side of the shear stress. But we cannot say that because the shear stress is negative, so we're forced to put a negative side here, right? We cannot do it in this way. Mathematically, we cannot do it in this way. So it definitely have some meaning here. So you can think about very, very easy things or very easy situation. Like this one. We know the shear stress the shear stress in, the shear stress out, right? Right, we do the balance in this way. So definitely, the shear stress has in and out, and it has its direction. Okay, its direction. So here you see the direction. So if you want to see the word to the shear stress, you cannot see in that way because you only have the shear stress of the fluid to the right, but to the word is in this direction, negative R direction, and that give you this one. Good idea. Let me say again. From the previous balance, we know the shear stress actually have its force direction and also its direction of transfer this shear stress. And then here, if we want to see the word, the fluid to the word, for this part, fluid to the word is in positive R direction, right? Positive R direction. But nevertheless, for this one, it's not, right? It's in the opposite direction. So that's why you have the negative side. Is that clear to you guys? And if you take a look here, then you can understand why the author is simply defined the direction from up to down as a positive direction. So when you try to calculate the shear stress here, you get a tau xz, but without negative side. Because it's in the x direction, correct direction. Sorry, here. It's here to here, right? You define x in here, so your fluid to the wall is in the correct direction. And this one is R direction, right? Even in the other side is also R direction, right? So you never encounter a situation that you need this negative side, except for this one, because for the inner tube, your fluid on the inner tube is definitely in the negative R. Negative R. So because you are in the opposite direction, you need to put a negative side here. Is that clear to you guys? Clear? Okay, good. Now let's move to the next example. So for this example, you will take a control volume very similar to the first example. So probably I will draw it. You just take a control volume. Okay, I will draw it and write down the equation. Except for the negative side. So you actually have a shear stress, not you. the fluid has just the force on the kappa r because in the opposite direction, so you have a negative side. So the force in the z direction are both in the positive side. All right? Because the shear stress here is negative, right? So you put a negative side, it becomes positive side. And negative is because it's in the negative r direction, so you put a negative side. It's not because you try to compensate this negative, so you put a negative side. All right? Hopefully it's clear enough to all of you. All right. Because I'm a very bad drawer, so I use this figure and try to mimic it, okay? So I can draw in a better way. That's one. This. And this. And this. Okay, good. So we have a control volume in this way. Sorry. It should not be in this way. It should be in this way. Guys, pray. This way? Okay. Is that... I try my best, okay? So we put this as z direction. And this one is s direction. Okay? So we have delta x here. And we have arrow here, I think. And we don't care about the y direction, okay? So we have arrow and delta x there. And let's write down the, probably we also put although we don't care about the y direction, we still need to get we still need to specify the size of the control volume. So we use W arrow and delta x. Okay, I'll try to plot this. Hopefully it's clear. It's not that bad. Okay, so let's write down the force balance. be able to write down the two equations. Why I only do one balance? Think about that why I only do or take only one control volume. I'm supposed to take two control volume. Alright? But I only take one. So if you don't want to take notes, think about that. Take notes. I probably need to take some waters, so I'll go to take some waters. Oh, by the way, I say some story to the class at night. It's about some logical things. I got to share with you guys. At that time, I share with them because I don't think. No, I shouldn't say I don't think. I think I have some probability to die in Korea. Because at the time, my flight to Korean is in a situation that the North Korean seems to want to do something to the South Korean. And I'm so scared about that. So I say something to the student in the other fluid mechanics course. It's about very interesting logic. You can think about that and you will find something ugly. Not ugly, bizarre, sorry, not ugly. You'll find something bizarre, you'll find something strange. You feel, it cannot be in that way, how can it be? So many of many of us may complain about things, but when we complain about the school or about the instructor or the government, we are not really want them to listen to us, right? We just try to complain. You will not go to, normally, you will not go to the president office and then tell him that what kind of things he do wrong. No, you don't do it that way, right? No. So but when you complain to some being, celestial being, I mean some being in the heaven, like you complain to the heaven, you really want the being hear you, right? It's different. It's different. It's kind of interesting. It's different things. But funny thing is this: if you do that, you really want something hear you, then the first thing is you believe something is there, right? Something is there. Otherwise, you will not want something to hear you. So you believe something is there. And second is more interesting. You complain to him. It means you believe he has power to change things, right? Right. But if you think about this, you compare this logic to the real world, you find there's something stranger. Just like you don't go to the president's office and then complain the president in front of him. You don't do that, right? Why? Because you're afraid of him. You know he can control so many things, so you don't do it that way. But you complain to some being, you are not afraid of that? Kind of interesting, right? You already believe he has power, even larger than the president. But for the president, you don't do that. So think about that. So what kind of things happened? And one explanation from the philosophy, they kind of believe is this kind of relationship is more like the parent to the children. So that's why, as a human, we don't fear the higher order being. Okay, but you can think about this question. It's kind of interesting. At the first time I hear this from a philosopher, I think about this question for several days. It really shocked me. Really shocked me. So you can think about that by yourself. Anyway, I will come back to here. First thing is why I only do one balance and not two. Theoretically, I should do two balances, okay? Because this is two boundaries. They are not the same, okay? So I should do two balances. All right? The only reason I do one balance is I do one balance, and you can treat that I probably do a balance for the top bar or the bottom part. And then I should do the same, I should do the balance again for the other part. But at that time I realized that for the fourth balance, for these two parts, the equations for this fourth balance are exactly the same, so we don't do that twice. Okay? Okay, let me say again. Don't be fooled by the textbook. The textbook, they just try to write down one equation by one balance, and then they apply that to both situations. That is not correct. That is not correct. We should not do it that way. The thing we do in this way is you can treat that is we do the balance for one part, and then after that we should do a balance for the other part. Nevertheless, when we try to do a balance for the other part, we realize that equation is exactly as the first part, so we don't do that again. All right? Okay? Okay, get the idea. Okay, good. So we do only one equation because for both of them, if you do a balance, you get the same equation. But it doesn't mean that you apply one equation to both of them, okay? Right. Okay, so we have the control volume this way. I drew this, and hopefully it's clear. So z direction is in this way. So it's in this way. This way. This here means that there, okay? And you have the y direction is inside here. That's W. And your x direction, delta x. And note that you take control volume for the first part. Not both of them, only the first part. And after that, you try to do the second part, you realize they are the same, okay? So we only do that for the first part. And then we have LW, this one. So what's this? This is the area multiplied by the combined momentum flux, or the phi xz. It should be the x. So phi xz should be transposed in this direction, right? Because phi xz. So we should multiply by LW, so the area of this, to the phi xz, and get a force. Okay. And second is phi z. Phi z is in this direction, right? So we should multiply by W and delta x. So W and delta x, element phi z. Hopefully it's clear to you guys. And then we get this, then is there a gravity? For this, for the direction of the flow in this way, and the gravity is this way. So gravity should not contribute any to the flow, right? Because the flow is in z direction, and gravity is in x direction. And we are doing the balance of the force in z direction, right? Because phi z, phi z, they are all the force in z direction. So we are doing the force in z direction. Probably I should write down here. Okay, and gravity is in x direction. And since the x direction and z direction are perpendicular to each other, so the gravity does not contribute any to this flow. Okay, so we don't have gravity here. We have 0 here. And after this, we do the same thing. We divide the equation by LW delta x, and then that delta x approaches 0. So we divide LW delta x, and that delta x approaches 0. And also we put these two terms to the other side. So we have the x plus delta x minus x equal to x, phi xz x equal to x. Then divided by delta x, and delta x approaches 0. And for the other side, we have this one, this, right? So we have L, and phi zz minus phi zz, z equal to L. So we have this equation. And before we further deal with this equation, we should do some analysis on the phi z and phi zz. So phi zz, we know that it should equal to p plus tau zz plus rho vz vz. And similar to the previous example, if it is a laminar flow and you have the same cross-section area does not change, which is the case of this example, your vz does not change along with z direction. Okay? So in z direction, the vz should be the same. If that's the case, the rho vz, rho z, this term, should go to 0, since z does not change with the VZ does not change with the Z direction. And also, if you put this into here and here, because VZ does not change along with the Z direction, so these two will cancel out this term, right? Cancel out this term. So this term also cancel out. And but this, we will have that. Why? Because it's two plates, right? Two plates. And your liquid is flow between two plates. Between two plates. And if you compare to this one, you realize that's different. This one is exposed to the atmosphere. So the P upstream and the P downstream should be the same. Okay? But for this one, it's different. Your P upstream and P downstream, there's no reason it should be the same, okay? So you should have some P here. Some P here. And that's the only thing will contribute to here. Alright? So if we put a P here as P0 and P here as PL. So here we only have P0 minus PL divided by L. Alright? Okay. And left-hand side, we know there is no Vx, right? No Vx. No this one. We have Vg, but we don't have Vs. It's laminar flow. So if we don't have Vs, the left-hand side only have this tau xz. And the right-hand side only have that P0 minus PL divided by L. Okay, so let me write down the equation. Any question, anything you want to ask? Okay. By the way, I have the other things I want to say about the pufferfish. So, if you really want to try the pufferfish, I would suggest you try as soon as possible. But after you try that, don't try to eat that too much. Okay. So the pufferfish, they get a toxic material from outside. They are not like snakes. The snakes they create the toxic materials, but pufferfish is getting the poison things from outside. In other words, those pufferfish can be eaten because they did not feed those pufferfish with poisoned foods. Okay, so think about that. We can eat the pufferfish because the pufferfish does not eat any poisoned food. It is very likely in the future. Some people will neglect these important things, and then they will feed the pufferfish with natural food. Not a food that prepared only for. Not a food that prepared, so it does not have a poisoned material inside. So if they feed the pufferfish with some natural materials, they just get it from the ocean, the pufferfish will become toxic again. And at that time, if you eat the pufferfish, you may get poisoned. Okay, so I still suggest you don't eat that kind of food. It's dangerous, and it can easily kill a person. Okay? All right. Anyway, hopefully my explanation is clear enough about a pufferfish. So at the very beginning, I saw the eatable pufferfish is a special species that can be eaten because it does not generate the poison material. But after I understand the pufferfish can be eaten because the pufferfish never generate poison material. It eat that from outside the environment. And if we don't feed the pufferfish with poison material, then the pufferfish is not toxic. So if some people they make mistake, and then they feed the pufferfish with natural materials, which definitely including the poison materials, then the pufferfish will be poisoned. And then if we eat that, we may die. So my suggestion is don't eat the pufferfish, okay? It's not delicious. Anyway, let's come back here. So as I explained in the beginning, that we are not trying to do a balance for both region at one time, okay? We just try to do the balance on one region, and then we get that. And then we say that similarly, we can get the equation for the other region. And lucky to us, these two equations look similar to each other, okay? And then we try to solve that. We should have two integration interval, right? Integration interval. And then we apply our boundary condition. Know that we have one boundary condition for shear stress, 3 for the velocity, right? So we apply the boundary condition for shear stress. And luckily, we realized that the C1 actually equal to, the C1i equal to C1 double I. or C1 equal to C12. Okay, and then we assign C1 to it, to both of them. Any question of this? No? Then we can write the equation for the velocity, but let's keep that there, okay? Let me see how to fill this 5 minutes. Let me erase it. How about we think about a question that we deal with the previous question? So if okay, if we want to calculate the force of the fluid, on the wall, what will happen? And if we take a look at this, we realize that similarly to the previous example, we will have one shear stress with negative side and the other with the positive side. Okay, so if we calculate that, the force to the we actually have our shear strength now x equal to minus b. And multiplied by the area, that should be LW, and with the negative side, and then plus the second one, and also LW. Right? If we get a C, but we will get C next class. Okay. But here we still have this negative side, right? Still have this negative side. Because the direction of the x is from here to here. But this force transformed, we want to calculate is liquid to the wall. So it's in the opposite direction of the x, right? In the opposite, because liquid to the right, to the wall. So in the opposite direction. So you have the negative side here. But for the second fluid, it's from here to here, right? So it's in the positive direction. So you don't have negative side here. So, okay. And see you next week. And have a good weekend.